morning. We begin. Lecture number 14. Our plan is to complete our discussion of systems level aspects. We've talked a lot about the handoff aspect in the last lecture. We've now started to explore more specifically the aspects of the wireless channel, understanding the large scale effects, small scale effects. So let me just quickly run through the key points that we have highlighted in the last lecture. So when we talk about handoffs, there's a whole range of topics that we have covered, all the way from the control plane, understanding how handoffs are handled by the system, the role that the mobile plays in the whole handoff process, because the measurements are reported by the mobile assisted handoff, the design parameter delta, which tells you how much. So this is the threshold at which you start searching for base stations for possible handover. The larger the delta, the more robust your handoff mechanism is, but that also means more handoffs in the system. So therefore, that's a trade-off that you must do. So this is a key parameter that we must keep in mind. We do not want ping-pong handoffs, so that we have introduced a hysteresis into the system. We also keep track of the fact that there are high Doppler users, high velocity users who may need quick handoff. And as we mentioned yesterday, high Doppler does not necessarily mean that that you will have a handoff. But these are, sorry, the other way. Low Doppler does not mean that you may not need a handoff. But high Doppler cases definitely are things that you have to be careful with. The wireless channel has several effects that are different from the AWGN channel, which we have studied extensively in digital communications. And yesterday we started to introduce some of the aspects of the wireless channel. So again, to remind ourselves, we have a complex baseband representation of the transmitted signal. We have a complex baseband representation basically carried over into the receiver side. We also have this in between, what we call as the channel. So let me draw this. In digital communications, this would be called as a channel. The channel is characterized by a symbol-spaced equivalent filter. So basically, all of the impairments are captured. What we need to understand is how does that change when we want to go into a wireless channel? What are some of the elements that we need to keep track of? So we will also take the same route as representing a complex baseband equivalent of the propagative channel, but it is very customized to our understanding of the wireless channel. So the link that we are focusing on is between a base station or a mobile, or in the uplink it would be mobile to the base station. We said it's a point-to-point link. That is what we are interested in characterizing. There are some differences, but by and large, the behavior of the wireless channel does not differentiate who is talking to whom. The impairments are the same. So some notation that you will see in the 4G literature. The word base station is not used. They use a acronym called E node B. Node B, B stands for base station. And on the mobile side, on the receiver side, a mobile station is called the user equipment, UE. So in 4G, there is some different notation, but we are looking at that aspect. We would like to get a equivalent baseband representation that helps us understand how the signal is impaired when it propagates through the channel. What are some of the ways in which we can rectify those and then and get a good performance out of the system. So that is our goal for today. Let me quickly review the points that we have made in the last class with respect to the differences between large-scale effects and small-scale effects. Large-scale effects are of the order of hundreds of meters. So these are changes that happen when you move over substantial distances. On the other hand, small scale effects are very much in the vicinity of the order of 10 to 20 lambda. And again, we have looked at what is the typical values of the lambdas that we are interested in. It is under 1 meter. So therefore, these are small perturbations in your position. In terms of the large scale effects, we mentioned yesterday that the non-line of sight transmission, which is primarily what we will have in the wireless channel, takes place through three mechanisms: reflection, diffraction and scattering, of which the more dominant ones are the reflection and the diffraction. Scattering gives you a component, a significant component, but it is not as large as the other two. Now, based on what aspect of how much of reflection, diffraction and scattering is happening, we would have to characterize it for the specific environments that we are looking at, either a indoor environment or an outdoor environment, and all of these are captured through propagation models. And we mentioned yesterday the Hata model is one such example. Again, once you have understood one of those models, it's more or less to say that, okay, I know how to apply these models, and we will take some time to look at one of the models at a later point. But as of now, at this point, we already know how to handle the breakpoint model. The breakpoint model is one of the propagation models that you can use. So having implemented one of those, you can substitute for the breakpoint model with something else. Because the propagation models essentially are telling you how to calculate PR of D. At a distance D, if you are transmitting with a certain power, what is the received signal power? Because that basically tells you then the range and all of the other calculations. So any method that tells you how to calculate PR of D is okay, because we know how to do it for one model, we can do it for any others. But keep in mind that there is a lot of sophistication in these models. They take into account whether you are indoor, outdoor, whether it's a rural environment, whether it is a high-rise type of building, whether it is a dense urban environment. And so there are lots of variations in the propagation impairments, and all of those are captured in the different models. So again, that's an important area of study, not to minimize that. But again, from our approach, it says it is a model that tells you how to get PR of D, which is sufficient for us. Now, line of sight happens only in what we call as the near field, when there is no obstruction. And depending upon the height of the transmitting antenna, this could be 10 meters, 20 meters, maybe even 100 meters. But again, it is not all the way to your destination, target mobile. So therefore, we do have designed the system to be a non-line of sight system. That is our basic design. Now, large-scale effects, I believe, are to a very large extent affected by, one is propagation. Propagation would primarily be dependent on your propagation parameter, N, what are the different losses that you have, the height of the transmit antenna, H of the TX antenna, the height of the RX antenna. So these are all parameters that will affect the propagation model. But at the end of the day, what else affects the signal quality? That is where we pick up shadowing. Shadowing is not the one created by the channel. This is obstructions that are in the path, other buildings. Or maybe you're in the basement of, or you're going through a tunnel. So those are the things that are not necessarily caused by the wireless channel, but the fact that you are in a disadvantaged position. So these are primarily obstructions. So today what we would like to do is try to understand a statistical characterization of the obstructions or shadowing, and then say that, okay, that is the right way to do it, because we don't have a deterministic scenario. It is a scenario where there is a lot of variability. You may be inside a building, outside a building. So there are certain things that we have to characterize using statistical methods. So with that understanding, we move over to the small scale effects. Now, small scale effects, as we talked about earlier, is caused primarily because of this phenomenon called multipath. Because the signal can bounce off different objects and arrive at the receiver. Now, depending upon whether there is time separation between these multiple paths, you may or may not have time dispersion. If you don't have much time separation between them, then all of them will arrive approximately within the same time, all the multipath components. Then you get what is known as flat fading. So flat fading means no dispersion. Frequency selective fading means that there is a time dispersion. And again, why frequency flat, frequency selective? Maybe you already know the answer. Why do we use the terms frequency flat, frequency selective? Okay, so if you want to have something that is spectrally flat, what should be your time domain signal? It must be an impulse. An impulse in the time domain, if this is time, this in the spectrum domain will basically give you something that is flat. Okay? So if you want to have a fading that is not dependent on frequency, then your effective channel impulse response must be one tap, because then all frequencies have the same gain, that basically the gain of that single tap. Now if I have a second and a third tap as part of my impulse response, then what happens is the frequency response of this filter now comes into play. It may have some behavior like that. So some frequencies have gain, some frequencies have attenuation. So basically when you have only a single tap, you call it frequency flat. That's the same as non-dispersive. So non-dispersive, same as frequency flat. Dispersive, same as frequency selective fading. Okay? Frequency selective meaning different frequencies experience different gains. Then there are several variations of the types of fading that we can encounter, statistical characterizations. We have the Rayleigh distribution, Ricean distribution. There's also something called the Nakagami distribution. All of these are characterizations of the nature of the signal and the fluctuations that you will experience in the signal. That is something that we will study as well. Okay? There are some other aspects such as random FM, which are not very significant, so we don't really focus on those, but these are the large, this is the significant ones within the small scale fading. Okay, let's move on. Lots of interesting ground to cover today. Now the non-line of sight basically means that there is no direct path. You would have to go through one of the three mechanisms that we have, either diffraction, reflection or scattering. Each of them contributes a certain component to the signal. For example, reflection probably can give you a stronger component than diffraction, because diffraction is based on Huygens principle. It says there is a creation of secondary waves, and therefore what actually goes towards your antenna may be a smaller component. But nevertheless, each of these can be characterized. Again, in Rappaport's book, it's well done, and maybe towards the end of the course we will spend one lecture just to sort of highlight the aspects. But this is something that I believe most of you are familiar from the studies in physics and studies in electromagnetic waves. So let's now focus on the shadowing aspect. Again, this is a figure that we have seen previously. What we are trying to do is trying to understand what is the impact of blockages. For example, if you had a blockage, a building here, suddenly when you go behind the building, that is the building is between you and the base station, then you see that there is a drop in the signal. So given that there are such obstructions, maybe a tree, maybe a building or a bridge, whatever it is, that reduces the signal strength, which effectively says in this along this direction your range is not the same as when there is no obstruction. So in a way of characterizing it, typically you would think of it as an omnidirectional antenna, that your range is some average radius. But in reality, what happens is because of obstructions, there may be, in fact, if you have an extreme case of an obstruction. So, for example, you may even, your coverage at some point may actually be, there may be a scenario where there is a significant reduction in one direction because of a very big obstruction. So, by and large, we want to understand this sort of characterization, and it is helpful for us to keep that picture in mind. So the essence of shadowing is captured by the following statement, that the path loss at a distance d, we want to characterize it as some path loss at the distance d average value. These are all in dBs, plus a random variable x sigma. We said that this is a Gaussian is a good approximation to this. So basically it is some mean value with some perturbation which looks Gaussian in its behavior. So this is where we begin. X sigma is the random variable. It is a Gaussian, has a Gaussian distribution. It is zero mean, because you can have from the average signal point, you can have more path loss, or you may have less path loss. So basically there are some variations possible. When can I have less path loss? If for some reason I am at a higher height, right? Because let's say you are in a position where there is like a small hill, and you happen to be there, you will actually get an advantageous position. So again, shadowing can go both ways. There are scenarios where you get obstructed, there are scenarios where you get benefited. So it's a zero mean Gaussian, the standard deviation is sigma. Okay, so our goal is to study this mechanism and to understand it fully. So shadowing is what we are trying to recognize, and notice that when I write the equation on a dB scale, I got the following expression. So this X sigma has got a very unique name. It is a random variable that is Gaussian in the log domain, okay, because basically it is X sigma is represented in dB. Such random variables are called log normal, because they are normally distributed but in the log domain. So let's quickly characterize the log normal random variables. So if I have a variable sigma, which is 10 times log base 10 of sigma dash, sigma prime. Okay, that is my, so sigma prime is a random variable. I have taken 10 times log base 10. Now the random variable sigma dash has is said to have a log normal distribution. Log normal distribution under the following conditions. If when you go to the logarithmic domain, omega has a Gaussian distribution, Gaussian or normal distribution. Okay, Gaussian or normal distribution. Okay, so that's the basic definition. So I am looking at a random variable which is Gaussian in the log domain. Therefore, its underlying random variable is a log normal. So that is why whenever we talk about shadowing, you will hear the term log normal shadowing. Okay, so it is Gaussian in nature, but it's not Gaussian in the natural scale, it is in the logarithmic scale. So we always refer to as log normal shadowing. And the reason and the underlying explanation for that is given in this fashion. So given this understanding, what is the distribution, the probability distribution of f of sigma? It is Gaussian. So it is 1 over root 2 pi sigma omega e power omega minus mu whole squared divided by 2 times omega 2 times sigma omega whole square. Basically a Gaussian distribution. Okay, so this is a general one, but normal basically means that mu equal to 0. Sigma x is the only one that remains. So I think I should write it here with x. Okay, mu is, it's a zero mean Gaussian. So therefore, what you are left with is only the standard deviation expression in the equation. Okay, so now I want to translate it into a meaningful, useful tool. So the tool that we are going to focus on is probability of outage. Now, how does the fact that I have characterized this particular impairment as a log normal impairment, how is it going to help me understand the aspects of the impairment? So here is what we would like to look at. So the received signal strength, received signal strength at a distance d is given by the transmitted signal power minus the path loss at a distance d. That is the, but we also have another equation which says that my received signal power is equal to the path loss at a distance d is the path loss at a distance d plus x of sigma. Okay. So, using these substituting the expressions for the for path loss. So, if I have this as equation number 1, equation number 2, I substitute it into this equation, you can see that we can write down the following expression. The received signal power at a distance d can be written in terms of the received signal power at a distance d average, that means with the average path loss, minus x sigma. So, path loss had a positive, like if you think of it as a positive addition because of shadowing, that means your received signal power is going to be less by the same amount, and that is what this equation tells us. Okay. Now, you may wonder, really does not seem like we have done a whole lot, but this is a very, very useful equation and a useful expression. So, now let us move into the aspects that we want to explore. So, the probability of outage. Probability of outage, as we had described earlier, is the probability that the received signal received signal at a distance d, well, maybe I will write this as PROB, so you do not confuse between. So, this is the probability that the received signal strength at a distance d is less than the threshold P min. Okay. Now, which if I substitute in the using the equation from the previous page, this is the same as the probability that the average signal strength PR of d minus x sigma, that means because of the shadowing, is less than P min. Okay. Now, this gives me a very, very interesting rewrite of the equation. This basically says x sigma is greater than PR of d average minus P min. Okay. I have just rewritten the variables. But the insight comes from this, because what is PR of d minus P min? That is my margin. So, actually this equation has not given us anything new. All we are saying is, if your shadowing is greater, if the reduction of signal due to shadowing is greater than the margin, of course you are going to go into outage, right. So, there is, it is a very simple equation. But here the benefit, all the things that we have done now comes into play, because x sigma is a Gaussian, and for a Gaussian I know how to characterize. So, if I call this as beta, so if I ask you what is the probability that a zero mean Gaussian is greater than beta, then you will say that this probability can easily be done 1 by root 2 pi sigma. You will integrate from beta to infinity e power minus x squared by 2 sigma squared dx, right. That is your cumulative value starting from beta if you go all the way to infinity. Now, one more step, and then we have a useful tool for us to understand and implement. That is basically a change of variable, where I want to introduce y is equal to x by sigma. So, if I introduce that notation, this becomes 1 by root 2 pi, please do the change of variable. This becomes beta by sigma. This will become infinity remains as infinity e power minus y squared by 2 dy, and this is a well known expression. This is the Q function at the value beta by sigma. Q functions are well known. You have used it in digital communications. It is something that we are quite familiar with. There are tables that are available to us, or you can also compute this expression. Now, some people are not as familiar with the Q function as the complementary error function. So, Q function and the complementary error function are actually related, and you can map them. So, the complementary error function is ERFC. Basically, if you look at the definition of the Q function, the definition of the complementary error function, I would like you to please verify the following result, again more as a refresher of what you have already studied. So, basically the complementary error function for a parameter x is the same as 2 times the Q function with root 2 x. So, if you calculate the Q function with root 2 x and multiply it by 2, you get the same as the complementary error function. So, as a function, these two are more or less representing the same. The Q function is very intuitive for us because it goes from one threshold to infinity of the normalized distribution. Okay. Now, but what did all of this give us? The following. This is the Q function of PR of D bar minus P min divided by sigma. Now, notice that we said that the shadowing is described by means of a log normal distribution. That means in the Gaussian domain, it's 0 mean, it has got a standard deviation. You always have to specify. So, you will never find a statement which says the shadowing is log normal and that period. They will never specify the mean because it's assumed it's 0 mean, but the standard deviation is always specified. Why? Because standard deviation is one that is going to play a very key role. Sigma has to be specified. So, now we have the understanding that the perturbation of the path loss is a random variable x of sigma, which is Gaussian. If I write it in the dB domain, it is Gaussian, it is 0 mean, and it has got standard deviation sigma. And these are important parameters for understanding the shadowing aspect. Okay. So, now maybe to anchor all of what we have said so far, let us look at an example. The example will help us consolidate whatever we have said so far. So, the example says that the receive sensitivity that my system is designed for is minus 110 dBm. So, this is my P min. I should make sure that I don't exceed, I don't go below this threshold. I have designed my system with a margin. So, the statement, next statement I would like for you to interpret. My statement is that the mean received signal power at cell edge, at the edge of cell, or whatever I consider as the edge of my coverage of my base station, is minus 100 dBm. Okay. So, this is on average, this is the PR of D bar. Okay. What have I done? How much margin have I given? 10 dB margin. Okay. So, the margin that I have designed my system for is 10 dB. Now, is 10 dB good enough, or 10 dB is not good, too much, too little? The important question will be, what is the standard deviation of your log normal shadowing? So, log normal shadowing we are given has a standard deviation in this particular example, just for illustration purposes, has got a sigma of 10 dB. So, standard deviation is 10 dB. I have given myself a margin of 10 dB. Now, the key question is, what is the probability that I get good signal quality? What percentage of my edge of cell gets good signal power? Okay. So, basically this is a question that, so what percentage of the cell edge has good coverage, has acceptable coverage? So that is the problem that we have to design for, and again it's a very, very practical computation that you want to understand, has acceptable signal quality. Okay, so we just are one step away from the answer, because the probability that you have good signal is the same as probability that your received signal at your cell edge, let's say that's at a distance, I think we have been using R as our, let's be consistent, of your cell edge, the average of that, or no, the received signal at your cell edge must be greater than or equal to P min. That is the condition that we are being asked to characterize. Now a PR of D at a distance D we know is given by PR at a distance R average value minus X sigma. So again use this information which says this is the same as saying the probability that X sigma, in the previous case I was talking about outage, this time I was talking about good signal, that your your shadowing is less than the margin. Basically we are asking the complementary question. So this is less than or equal to PR of D average minus P min. This is my basically this is still my margin. So the question is being asked in this particular problem is a complementary one, but exactly the same thing. So the answer would come along the same lines as before. It would come in the form of an integral 1 by root 2 pi sigma. Now what are the limits of the integral? Minus infinity to beta, minus infinity to beta e power minus y squared by 2 sigma squared dy. Okay. Now if I wanted to convert it into a Q function, then I would do a change of variable and get it into the normal form 1 by root 2 pi minus infinity to, I can do two things. I can just do the scaling. I can also do a change of the sign. So I can also do minus y by sigma. So if I do both those changes, again just I am sure you are very comfortable with those types of manipulations. What you will get is minus beta by sigma, minus beta by sigma going all the way to infinity. So minus infinity becomes plus infinity, beta becomes minus beta by sigma e power minus u squared by 2 du. Okay. So basically if I were to look at the continuum covered by the variable u, this is 0. We are asking for the integral to go from minus beta by sigma, minus beta by sigma. So this integral is q of, so basically we are asking for this integral. So this integral is nothing but q of minus beta by sigma. Am I right? Okay. Yeah. Yes. So that's the way to interpret a q of a negative value. You interpret it in the following way, because the Gaussian the normal distribution is symmetric. There is a point which is beta by sigma. It's the same, integrating from minus sigma beta by sigma to infinity is the same as integrating from minus infinity to beta by sigma. That is another way of doing that. And integrating from minus infinity to infinity is 1. So therefore what we say is the integral from minus beta by gamma all the way to infinity can, because of symmetry, I can take it as 1 minus this, so which basically says that it's 1 minus q of beta by sigma. Okay. So basically q of beta by sigma will go from here to here to infinity. 1 minus that is the integral value that we are interested in, because this and this are yield the same value. Okay, and 1 minus the cube of beta by gamma gives us the same value also. Okay, Now, these are gestational things. In case you're not familiar with the Q function, just spend a few minutes and you should be able to get the following expression. So, this is the probability of good signal. The probability of good signal is given by this number. So, let us try to interpret it and try to apply to get some insight out of it. Always our examples are intended to produce some good understanding. Okay. So, what is beta by sigma in our case? Beta by sigma, beta says it's the margin. My minimum signal strength that I've designed my system for is minus 100 dBm. My P min is minus 110 dBm. So, my margin is actually 10 dB, minus 100 plus 110 divided by sigma. The sigma is also 10. In this case, my beta by sigma came out to be 1. So, probability of good signal under this condition, under the assumptions that we have made, good signal is given by Q1 minus Q of 1. So, basically this is given, this you can look it up in the tables. This comes out to be 0.841. So, 84% of your cell boundary has got good coverage. So, how do we visualize it for intuitive purposes? Think of the cell boundary as a small annular region. We don't know exactly where these outages will occur, but what we are saying is the shaded portion, those portions are shaded, are places where you have outage. It is approximately 16% of the cell boundary has got outages, and the rest of the parts are good signal. Okay, this is outage portions, and again, that is why at these points, if you want to actually look at the coverage will actually go in, because at the boundary you don't have good coverage. So, the coverage actually ends before you reach the boundary. So, at these points you will find that the cell coverage is actually going in. So, the intuitive understanding and the mathematical characterization come together to help us understand what is the impact of shadowing. Where will it affect you? It can affect you anywhere in the cell. But where do you want to characterize it? I want to definitely characterize it at the cell boundary, because I want to know what percentage of my cell boundary is going to have acceptable signal strength. So, let's try a few variations of the example. Again, this is more for practice. Suppose my received signal PR at the cell boundary, PR of R bar, I had designed it for minus 110 dBm. Okay. Is this a good design, bad design? What is my margin? 0. So, that means what do I get? I get Q of 0. So, what is the probability that I have a good signal? 0.5. Only 50% of my area is going to, because I have not designed for margin. So, and because a Gaussian perturbation, so half the time it will be higher, half the time it will be lower. Probability of good signal, well, I shouldn't say good signal, it should be acceptable signal. Probability of acceptable signal is only going to be 0.5. Okay. Now, let's push this a little bit more for clarity and for reinforcing what we have studied. So, if I knew this was the problem and I actually took extra precaution to design it for at minus 90 dBm, then my beta by sigma comes out to be 2, and in such a case the probability of good signal is 98%. Okay. Or let me write it the other way, the probability of outage in this case is approximately 2%. Again, a very good design. So, what does it tell me? Make sure you know what is the standard deviation of your shadowing, and accordingly design your margin. So the last example actually reinforces the statement that I just now made, because if I knew my sigma was 5 dB, standard deviation of my shadowing was 5 dB, then I know that PR of R bar equal to minus 100 dBm will give me beta by sigma equal to 2, which will give me the same outage probability. Okay, why did I do that? Because I know that my standard deviation is only 5 dB. So therefore, I can be a little bit more aggressive in terms of my margin and reduce my margin and still expect to have good signal quality. Okay, so as I mentioned, all the mathematical tools that we are going to develop is to make sure that it actually addresses the physical problem that we are working with. So intuition and the mathematics has to go hand in hand to help us understand and work with the mechanisms that we are facing. Any questions on the aspect of the characterization of the shadowing? And also, how do we interpret the margins in light of the standard deviation? If you anything which is puzzling or not clear, please feel free to ask. Okay, so now we have addressed the issue of how the outage probability gets affected by shadowing. Again, we will come back to talking about the propagation models. Propagation models are more of a somebody gives you a formula or a graph, and you use that to calculate PR of D bar. So basically, all the propagation models are giving you is the received signal strength at any distance D average value. This is what the model is going to give you. Now on top of that, you have to say that I am going to have PR of D minus X sigma. I need to know what is the standard deviation I need to know. Based on that, based on what is the quality you want to satisfy, let us say you want to have 2% outage or 5% outage at your cell boundary, you then know how to design your beta by sigma, which then tells you what should be your value of beta, which is your margin. Okay, so it's a very, very useful tool. It's a combination of path loss model and our understanding of what shadowing is doing in terms of the additional impairment that it introduces to the path loss. Okay, now we go back to our small scale fading. We move over from the large scale to the small scale effects. So small scale effects. These are the perturbations of the signal that, that come about because of small movements of the order of 10 lambda to 20 lambda. And obviously these are things that are affected by two things. One is multipath, the other one is my mobility, the Doppler. So let's get a basic common understanding of Doppler so that all of us are on the same page as to what we refer to by Doppler and its impact on us. So here is the base station, the mobile. This is the direction of propagation. Now if it turns out that my mobile is actually moving away from it radially in the direction of the propagation of the electromagnetic wave, then and it's moving with a velocity v meters per second, then I get a reduction of my my carrier frequency because I'm moving away by the Doppler. F Doppler is my shift in the carrier frequency. It looks like I have a frequency offset because my Doppler got shifted. But in most practical scenarios, I may not be going radially away, I may be going at some angle. So this is V, this is the direction of the radiation, the radial direction, and angle beta. So the direction or the shift in the frequency in this case becomes Fc minus V cos beta by C, V cos beta by lambda. Okay, that's the shift in the frequency we will incur. Now lambda is nothing but the speed of light divided by the carrier frequency. So I can rewrite this as Fc1 minus V cos beta by C. Now, if I were going towards the base station, cos beta will become negative, and therefore I will get a increase in or a positive shift in my carrier frequency. Okay, so now I don't know which direction I'm moving. I could be moving towards the base station, I could be moving away from it. So for an arbitrary system, this is what we write down saying, I don't know the direction. So the Doppler shift for the nth component of the multipath, n stands for the nth component of the multipath. This is given by Fc into 1 minus V, that's the velocity with which I am moving, cos beta n, the direction of beta n. Again, it could be positive, negative, everything determined by this, divided by C. Okay, so basically our understanding is that each of the multipath components is a signal at a carrier frequency, but because we are at a sufficiently high frequency, these Doppler shifts must be accounted for, and therefore we look at the direction of propagation, direction of motion of the vehicle, and then say that this particular multipath component, which is coming at an angle beta to my direction of propagation, is going to have a Doppler shift given by this expression. Okay, so now going back to a very familiar diagram. So the expression that we have for this is R of t. R of t, the received signal, let me write it as R hat of t. R hat of t is the received signal. Again, this is basically showing that there is a line of sight. Okay, think of this as non-line of sight also. There are three paths. Each of them have got gains alpha 1, alpha 2, alpha 3, and because of their propagation distances, they have different time delays. Tau 1 is the delay of the first path, tau 2, tau 3. So how would I write down the received signal for this particular system? So it will be alpha 1, S of t is my transmitted signal. Transmitted signal. S of R hat of t is alpha 1 S of t minus tau 1 plus alpha 2 S of t minus tau 2 plus alpha 3 S of t minus tau 3. Okay, so that's my way of characterizing. Again, this is a modulated signal, so amplitude and the delay is what I have captured in this system. So in general, the alpha 1 and tau 1 may not remain constant because I am moving, so things could change. So this actually becomes, all of them become functions of time. So therefore, the gains are a function of time, the delays are a function of time, the number of multipath components is also a function of time. So the general expression for in the presence of multipath, in general, the expression that is given is summation over n, where n is the number of multipath components. It's alpha n of t S of t minus tau n of t. Okay, so this is basically the superposition of all the multipath components that we are encountering in the multipath channel. Okay, let me quickly get into the heart of our discussion. I want to introduce the complex baseband form. So S of t is the modulated signal or the transmitted signal, and this will be typically of the form a message signal m of t, a message component consists of m of t and theta of t, given by and where m of t is carried by the amplitude, and then the theta of t is carried by the phase. So cosine 2 pi fct plus theta of t. Okay, so the information or the message part is carried by m of t and theta of t, and the carrier is Fc. This is my carrier frequency. So the baseband representation that we develop must not have f of c. It should have m of t and theta of t. I don't want f of c because fc can be 950 megahertz, it can be 2 gigahertz, it really does not matter. So the essence of it is the baseband representation. So how do we translate from the modulated signal into the baseband? That the complex baseband is a one-step process, but you need to do that a little bit carefully. So let me just highlight the method. So expand this expression, m of t cosine 2 pi fct cosine theta of t minus m of t sine 2 pi fct, the quadrature carrier, sine theta of t. Okay. So now what I want to do is I want to leave out the terms containing the carrier frequency. So what I am left with is remove that from the equation, then I get the following complex baseband representation, which I am sure you are familiar with. Complex baseband representation says that my complex baseband signal is m of t cosine theta of t carried on the I branch plus j times m of t sine theta of t, this is carried on the Q branch. So basically the I component and the Q component of my signal. So this can be represented as m of t e power j theta of t, that is my complex baseband signal. If I call this as u of t, then the relationship that I am sure each of you is familiar with is S of t, the modulated signal, is given by the real part of the complex baseband signal u of t e power j 2 pi fct. This is the complex baseband representation of the modulated signal. So basically what I need to do is to take this S of t, and substitute into my multipath expression, remove all traces of the carrier frequency, then what I will be left with is a complex baseband representation of my modulated signal in the presence of multipath. Okay? So I would very much encourage you to try that substitution. It is not difficult, but you have to be careful in making the substitutions. And one more thing that you have to keep in mind is that when I substitute back each of these multipath components, they are coming in different directions. So therefore, for each of them you must actually apply the Doppler correction minus FDN. Okay, please make sure that it is no longer just the basic carrier frequency, it will be the carrier frequency shifted by its Doppler. So the complex baseband taken back, applied in a multipath environment, keeping in mind the Doppler shifts of each of those components. Okay, it's a simple step of substitution, but we have to do it carefully, because once you do that, then you get a very rich insight into what exactly is the impairment that you are fighting against. Okay, quick question. Yeah.
So what are you explaining when you drew those red arrows? I don't know that I can't find the relation between
these red arrows.
Yes.
Okay, basically the information, user specific information, is carried in m of t and theta of t. So the information content is carried in m of t and theta of t. Fc is the carrier. So that's the general representation of a. So if it was only an amplitude modulated signal, then it will be m of t cosine 2 pi fct. If it was only a phase modulated signal, it will be cosine 2 pi fct theta of t. But if you have both amplitude and phase information, there will be an m of t component and a theta of t component. Okay, thank you. We'll pick it up from here in the next lecture.